So in this section, we're going to take a look at another derivative shortcut called the chain rule, and this is specifically used for when we have composite functions, meaning we have one function inside of another one. So for instance, if I were to start with a basic line like 4x plus 1, and I decided to cube that quantity, this is an example of a composite function because we have inside and outside pieces. So this would be considered the inside function. And then since you cubed everything, that's considered the outside. So composite functions, we have inside and outside pieces. Now, there is some way for us to get around this composite function issue, if you will. So if we took a look at a polynomial example where we have something cubed or squared or to the fourth, we can simply write out that factor as many times as needed and go through a bunch of distribution to get an expanded form with no parentheses. So this might take us some time because you actually have to write it 3 times and go through a bunch of FOIL and distributions, but this is what we would get. So since this is in polynomial form, no parentheses, no roots, no fractions, we can simply just use our power rule shortcut to find our derivative as 24x squared plus 72x plus 56. So the chain rule isn't really necessary for this type of an equation or this type of an example, but notice how if I changed it to 2x plus 3 to the 100 power, you definitely would not want to go through 100 distributions or 100 factors to expand all of those. So this is when the chain rule shortcut can be very, very handy because it's a way for us to get here more quickly. So the chain rule, since we have inside and outside pieces, is comprised of both of those pieces together. And I'm going to write that out here just to have it in your notes, and then we'll go ahead and discuss it. So if we have some function comprised of 2 pieces, one of them of which is inside and the other one is outside, then the derivative can be found by taking the derivative of the outside function, which in this case would be f. We're going to keep the inside function the same, so notice how g of x remains the way it is, but then we're going to multiply by the derivative of the inside function, which we can write as g prime. So one way that I kind of think about this composite function chain rule shortcut is by thinking about onions. I know it might be a little strange, but maybe you want to use gobstoppers if you're a candy person. So if you think about a gobstopper or an onion, you have all these different layers going on with that particular item, and we're just going to peel away those layers one piece at a time, and specifically taking the derivative of each layer one piece at a time. So I'm hoping that kind of onion example helps us. Now, to show us how we can get to this result a little bit more quickly using the chain rule, we're going to try this process for the function. So our derivative, we would need the derivative of the outside function, and before we labeled that as the power of 3. So if we were to take the derivative of something that has a power of 3, we would bring down that power of 3, and the new power would be 2. So that's representing the derivative of our outside piece. We have to keep the inside quantity the same because we haven't really touched that layer yet. This is just like peeling away the outer layer by finding its derivative. So we took the derivative of the outer piece, we kept the inside the same, and then we're going to multiply by the derivative of the inside piece. So the inside for this example was 2x plus 3, and that derivative would be 2. So this is what the chain rule initially gives us. The derivative of the outside, keep the inside, times the derivative of the inside. So this does not match the previous derivative that we had, but we should probably expand this just to see that they are the same. So we could rewrite this as 6 times 2x plus 3 squared. And then if we square this quantity, we will get, 4x squared plus 12x plus 9. And then if we distribute in the 6, we'll get 24x squared plus 72x plus 56. So notice how it does match the previous derivative we had, and it should because we found the derivative of the same function by just using a different shortcut rule. So if we actually practiced this more complicated one that we thought was complicated previously, notice how that's not necessarily as difficult anymore. So the derivative of the outside would involve bringing down the power of 100. We're going to keep the inside. Our new power, since we brought the 100 down, would be 99, and then times the derivative of the inside would be 2. So we could rewrite this as 200 times 2x plus 3 to the 99th power. You could leave the derivative this way. I don't think I'm going to make you expand this 99 times, but that is a derivative nonetheless. So this chain rule is really handy when we have kind of inside and outside pieces or functions to take into consideration. Let's take a look at a trig example. So find the slope of the normal line if your function is sine squared. And specifically, we're going to use the point 3 pi over 4. Now, what's tricky about trig functions is we normally write the power after the trig function itself, but we should really be aware that this means the same thing as the sine function being squared. And I think by rewriting it like this, the chain rule is a little bit more obvious because we do have this outside piece and inside piece to take into consideration when we find the derivative. So let's go ahead and find the derivative itself using our chain rule process. The derivative of the outside would be 2, or the power of 2. So we'll bring down the 2. We'll keep the inside quantity. Our new power would be 1, because we brought the 2 down. And we have to multiply by the derivative of the inside, which would just be cosine. So if you actually want to rewrite this, this would be 2 sine cosine. All right, so there's our derivative. If we plug in 3 pi over 4, you may have to use the unit circle, but some of us may be familiar with it without the unit circle. The sine value of 3 pi over 4 is square root of 2 over 2. And the cosine value is actually the same thing but negative because we're in the second quadrant. So if we multiply those together, we'll have 2 out front. These fractions being multiplied together would be negative 2 over 4. So it looks like we have a derivative value of negative 1, but it wants the slope of the normal line, so we need the opposite reciprocal, which would just be 1.